So this is right about where we left off, right? We were talking about how we can think about the evaluation process. Because before, we were simply just taking the binary string and figuring out what its integer value is, right? But, so, like, let's think about it, right? The encoding is a binary string, and the problem is maximize the integer value, right? So, like, the problem space, as per our encoding, looks, maybe I won't try to draw the integer one, right? But like, think about all the possible values a chromosome could have in terms of its fitness if we're using the binary value, like the integer value, right? What are the total number of values? 0 to 1023 if we're using a length 10, right? So you could think like the chromosome's fitness can be anywhere from 0 to 1023. But I was saying last time, like we kind of ended, and some students kind of brought this up already. If you look at these two, in terms of, it's fascinating really, because there is the problem space, and then there's like the encoded space, which are not, like you want them to have like a relationship where you can go one way or the other. But, and we will use these words more, and I'm going to formally introduce them pretty soon, is there's this idea called the phenotype space. Phenotype is another word we stole from the biologists. Does anyone know what it means?
A representation of characteristics.
It's like the manifestation of like your DNA. Okay, so like your DNA, I am the phenotype. But my DNA is like the genotype. That's the other side, right? So in terms of, now really because it's such a direct representation, it's kind of hard to distill these two different spaces. When you have a very direct representation where your encoding matches the problem so closely, it's hard to distill these things. But you can still kind of do it. So in the phenotype space, in the explicit maximize the integer value, we've got, okay, all those different values. But when you really think about the encoding, we might be able to say like, well, hold on. Look at these two numbers. Which is closer to the optimal value of 1023? Well, if you think of it in terms of the integer value, 512 is. But when you really think about the encoding, 511 is way closer because the correct answer would be 1, 1, 1, 1, 1, 1, 1, 1, right? 10 ones. So this seemingly is quite far from the solution, even further than this one, quite far, even further than this one. So this would be better, but maybe if we start to evaluate these things, kind of like thinking more about the encoding, like what the encoding really means, we might have a better strategy. And notice that all of these things interplay. We have the representation, the search spaces, and the fitness, but the fitness actually somehow dictates which space, because like the fitness is a measure of how good it is in some context, like the space it is, the genotype space. So these things are all connected. Think about it like this. If I had let's say a 3-bit number, okay? I'm going to just a list of 3 zeros, okay? Because it's encoded as that list. I can make one change. One change gets me to like 0, 0, 1, 0, 1, 0, or 0, 1, no, 1, 0, 0. Go with me on that. Let me lower this for you. And then 2 changes, well, I could get like 0, 1, 1, and that could go from here or here. Or 1, 1, 0. That could come from here, or I could have 1, 0, 1. Well, that would be from like here and from whatever, there. That didn't turn out as well as I want, but I think you get the point that it comes down to like the distances. And then 1, 1, 1, well, all of them will go to 1, 1, 1 if we make the right one change. So we can see like, and like, okay, how did this really even like make sense? Like, how did we go from having, like here we've got 8 different solutions, right? 3 bits, 8 different solutions. How did we go from like, if we use the integer value, that'd be 8 different things. But now we're looking at like, so there'd be like 8 different unique fitness values. But here we've got like one unique set, another unique set, another unique set, and another one, right? We actually have only 4, like we halved. And in fact, that discrepancy, if we count the ones, and here's what I mean, right? Let's think integer value. What's the value of this? 0. Let me do it. Okay, this would be like 0. This would be 1. This would be 2. This would be 4, right? This would have a value of 3, 6, and 5, and this would have 7, right? So look, every node on this graph has its own fitness value. However, if we were to like break it here, this is the zeros, this is the 1s, 2s, and then kind of hard to see, but the 3, if we're only counting the 1s. So where do those fitness values go? Well, those solutions didn't go anywhere. It's just that they have the same fitness value because really, the distance or closeness to what I'm looking for is the same. Effectively, we're measuring what we said last time is Hamming distance. A very simple, straightforward version. Don't worry about memorizing that word, but like we would call that a Hamming distance. So there we go. So what if we change out here while I talk, I'm going to open up PyCharm. You know what? Take it easy. And apparently now I need to agree to something. Watch it make me log in again. Come on. Did you say please don't? Yeah. That's what I'm thinking. Because last time that was very challenging for me, evidently. Okay, so far so good. So here's what we can do. Let's change out. Cannot run Git. I'm not too worried about that. I use command line anyways. So, or for you, I'll use desktop. But let's switch out to the 1's fitness. What does that function look like? Pretty simple. Number of 1s, 4-bit in chromosome. Number of 1s, add the bit value. If it's a 1, add a 1. If it's a 0, add 0. It has no difference. And then return the number of 1s. Pretty simple, right? So by changing the fitness, we are actually really kind of changing like how we interpret the search space. Sometimes we'll use the word fitness landscape to describe how we can move through that space now. So if we switch this out, and all we have to do here is instead of value fitness, let's do 1s. Come on. Come on. Really? There we go. Let's just do that. Oh, and then at the end, we'll have to do that one too, I guess. Okay, so everything's the same. All I'm doing is changing the function that I'm using. I'm just changing the fitness function. That's it. So let's hit run. I mean, oh, wow. Obviously, now look at these curves now. They look a lot more like, well, it's kind of like easier to find those gradients, right? Because like one change will have a much like clearer, like when you have like the value of the integer fitness, like there's like a high resolution, right? Because like there'd be 1024. But if we're counting 1s, the best is 10, right? So now Like these curves look really nice now. I really like this. I'm guessing I still have elitism turned on, right? Like implemented, because there's no downs. And given that, like, let's try to remember back to what we did before, where bit string length is 25. Oh, so 20. Did I really not get the optimal? 22 is where I converged. Wow. Let's go to like 100 though, for fun. Population size 10. Okay, whatever. Now you might remember when we had like a generations of like 50 and whatnot. With the integer fitness, we really needed to crank those. If I remember correctly, we really needed to crank like the generations and population up to get an answer when we had like 100 ones, right? But now, okay, well there we go. Okay, we have a generations 50. I don't know, let's make it 100. Okay, we're getting there. The population size is a little small. Let's make it like 21. But also, notice how, like, those are nice curves now. That looks much nicer. I'm actually surprised. Wait, did we turn off? No, mutation still 10. Maybe we can make that 20. 92. I'm actually surprised we're not getting there yet. Then again, 100 bits is a lot. Like, what's 2 to the 100? A big number, okay? A really big number. Like if we did the value fitness, Python's going to be pissed calculating those integers, right? Now, fortunately, Python's kind of funny with integers, right? Like it doesn't have a fixed bit size. It'll like dynamically figure out how big it is, for better or worse. In fact, for those of you that were in 263, you might remember me getting mad about this because they're also like they don't use 2's complement. They're actually only 1's complement, but they have like, because it's a class, it's got like a field that's like, am I negative? It's a whole stupid thing. No, it doesn't. It's ridiculous. I love when programming languages are helpful, you know? Anyways, Python. I don't hate Python. It's just why you got to be the way you are. Let's crank up this a little bit, right? You know, we're getting there. Population size. Oh, let's make it 101. This almost certainly will get it, right? Yeah. There we go. We got a lot of hundreds, right? So this is nice. Whether or not, is this better than the value fitness? Is it not? Is it not? At the end of the day, the purpose of this is, remember, this is a stupid problem. You wouldn't use an evolutionary algorithm on a problem of maximize the integer value of some unsigned binary number. So you wouldn't use this, but at the end of the day, I think it quite clearly demonstrates, well, first of all, also we could see that this was kind of done around like generation, I don't know, it looks like we found best solutions around maybe 70-ish, 60-something, 70-ish, right? Not too bad. See what happens if we make it like 201. Do you think, so it looks like we got it around, here, let me undo it. I'm going to hit run a few times, and let's try to get a sense of where it finishes. You know, around 60, 70. That one maybe a little, you know, around 60, 70. Maybe a little less than 60 in that case. Let's say it's around 60, let's say. Just for fun, let's see if we make it 201. What do you think is going to happen? Are we going to find it earlier? Or, looks like we're finding it earlier. It looks like now we're getting it closer to like 50, right, by increasing the population size. And why? Well, as you increase the population size, think of the fitness landscape as a literal space, right? Every chromosome is a point in that space that's moving. The more points, the more likely you are to stumble upon the good area, right? But then again, having it too big has some cost associated with it. Like, what do you think the runtime is of this? If, like, look, when it comes to, if you want to know, like, what's the computational complexity of an evolutionary algorithm? That's kind of a silly question because it's, well, how long do you want to run it, right? The number of generations, that's linear in the sense that, like, I just set that as a parameter. The most computationally expensive part of your evolutionary algorithm is almost certainly, you can make an exception, you can do whatever you want, but almost certainly it's going to be your fitness evaluation. Now, ours are linear. Okay, it's a linear, but we've got a linear thing that we have to run on each member of the population for each generation, right? So that's really where it's going to be. So if you make the population bigger, that's going to take longer to run, right? And computation is a scarce resource, let's say, right? It costs energy, right? It costs runtime. Like if I'm talking about my example, like during my PhD, and I had like thousands of compute years, that was compute time I was using and someone else wasn't using, right? So there's always, like Canada only has so many supercomputers that we're allowed to use, right? We all have to share, so I was using a lot. I won an award. They gave you, I had to submit. Don't worry, I wasn't like stealing. I had to submit an app. Like everyone has access to it, but if you need a lot, you submit like a resource allocation request. And it's like a formal proposal, like a grant application, and then they don't give you money, but they give you in-kind computation resources. So they'd be like, oh, here, we're giving you $50,000 worth of compute time or something like that, right? And you're like, who decided it was $50,000? I mean, it sounds good. I can say on my resume, like, I got $50,000 of in-kind contributions. When was it really? Well, who cares, right? But anyways. So I wasn't stealing from anybody else, but anyways. It worked though, so don't worry. I got good results. All right, anyways. There we go. So experiment again. I definitely, like, look, I just did that one for us. I think it's probably good for today because 2/3 of the class don't know what we're doing right now. All right, so non-numerical hyperparameters. We often think of the hyperparameters of those values, right? Like what's the crossover rate? How many generations? What's the mutation rate? What is the number of, in my selection, the tournament size? All of those values, we often think of these things as the hyperparameters, right? Like these values, the things you can tinker with before you hit run. And that's absolutely true. But these are like the numerical hyperparameters. There's another type of hyperparameters which is very important to emphasize in evolutionary computation, because this is like, to me, it's not the whole point, but to me, it is a huge point of evolutionary computation. It is things like, what crossover are you using? Are you using 1-point crossover? Why didn't you use 2-point crossover or some other crossover, right? That's also a tunable parameter, but it's not a numerical one, okay? Evolutionary computation is a rough framework. Every doodad, every modular enhancement that you change out or you add to your algorithm are additionally things, they are degrees of freedom you have to change on your algorithm before you hit run. The way I sometimes like to think about it is like, imagine, does anyone here like play electric guitar? No, one person. All right, so I won't use that analogy. Let's say, okay, maybe I will use that analogy. So let's say you play electric guitar. Does anyone know what like foot pedals are for electric guitars and whatnot? There are these like little things, right? There'll be these like analog circuits. Electric guitars are all about those analog circuits, right? So you've got your electric guitar and you plug it into the amp, right? And what does the amp do? Well, the signal on your electric guitar is very little. So the amplifier takes the power and cranks it up to make the music that we hear, right? But it's a signal. And we can do whatever the hell we want to that signal between the guitar and the amp, right? Now, we could talk about digital pedals and whatnot and plugging it through a computer. No, we're not talking about that. So what people will do is they can plug their electric guitar into pedals that can have different effects. So what type of effect do I want? Do I want to make my guitar sound grittier, right? So we can manipulate the signal from the guitar to sound grittier by plugging in series my guitar. I'm going to draw a guitar. Ooh, right? Looks great, right? And here's my amp. It's the music coming out, right? We all know that's obviously music. Lovely. No making fun. This is beautiful. It's some real good music, all right? Great. So I'll plug my guitar into the amp, whatever, it makes music. Cool. But let's say I'm like, no, I want to make it sound like grittier. So I'm gonna take this pedal, this little modular pedal, like literally a pedal. Like usually it's like literally pedals you hit, right? So you want to turn it on, you want to turn it off. And a lot of these pedals, they don't just have like on-off switches, they have like dials on them, right? And maybe this pedal over here, this one's good, it does reverb or something, right? Like, ooh, it makes it sound like there's, something else going on. Maybe this one has a couple dials on it, right? And some cool blinking lights. And this one here does like an octave, right? So it also sounds like you're playing an octave above or something. Whatever effect you want, you can do whatever you want. The point is, these are these like little modular things that we can add to our signal to add a little bit more to it. Now, with a regular genetic algorithm, there's your standard stuff. Let's call your regular genetic, like whatever, it's your guitar. Your guitar has a couple of dials on it, right, that you can make it sound a little bit different. That's your GA, but maybe I think of like, oh, elitism. Let's add elitism. So I plug it into that, which is plugged into this, which also has a dial. And then there's another one here. Maybe it's got a couple like button switches, right? Maybe it's like very discrete values. And this plugs into here, and that plugs into here, and then this goes into my amp to make my signal the way I want. The point is, with evolutionary algorithms, it's like this. Any idea, any enhancement, any fun thing you want to do, you can add it. But a lot of times, those things come with dials that you have to set. So you can add some, but sometimes those introduce additional numerical parameters. Sometimes they don't. Something like elitism, sure, we could say, how many do you want to do? Often people are using one. So you could just say like, whatever, one elitism, there's no real dial there, fine. Some of them do add dials, some of them don't. Maybe some take some away. Maybe I don't like this one, I get a new one, I replace it with it. The point is, there's a bunch of dials that we can turn to manipulate our output. These are like the numerical ones, but these things themselves are the non-numerical ones. These are the things I'm changing out. Or maybe I'm adding entirely to enhance my algorithm. That was a good analogy, I think, right? You followed, right, with the guitar thing, even if you didn't know? Yeah? Cool. All right, so for the sake of time and and the 2/3 of the class, we're not going to go through this, which is really too bad. Yeah, so what I would like to do right now is I would like to say, crack open your algorithms, and then try to invent your own crossover function. I don't care what it is. You can do whatever the hell you want to do, but try to invent your own. How was it? Like just replace it. In the way that I just replaced the fitness function, what I would want you to do is I would want you to go down here, like write another crossover somewhere, and then down here, instead of calling, let's get rid of that, instead of calling 1-point crossover, you would call whatever you want. Now, this right here is one of the numerical parameters that we need to have for our 1-point crossover, right? Like how many things are we selecting? But yeah, so that's what I would want you to do. And then I would want you to do the same thing with mutation and selection. And then the question is, did it have a positive effect? Did it have a negative effect? Did it have a kind of an unnoticeable effect? All of those are entirely reasonable. You might be surprised how good the dumbest ideas are, right? You might be like, here's a silly idea, and the next thing you know, you're like, oh shit, it worked. A lot of times, right, you can approach these things two different ways. You can look at a problem and be like, I think this crossover is going to work on this problem because of X, Y, Z, right? And then you can implement it. Or sometimes you could be like, here's a crazy idea, let's see what happens. Annoyingly, often it's the latter that ends up getting good results. And the reason is we are using these algorithms for complex problems we have no other shot at. And often our ideas are just too naive. And we don't really know what's going to happen over time in this complex space. These are very complex problems and they're complex systems. It's hard to distill this stuff, right? By all means, try to apply method to the madness. But a lot of times, people end up just trying things that aren't bad ideas. Like there is a method to the madness, but it's not like if I were to, often what happens is someone tries something and it works, and then they go, okay, why did it work? They'll rationalize it more after than before. They'll have some rationalization before about why they think this is a good idea, but it's not like this well thought out formal proving thing that like this is going to work. Here's why it's going to work. As often you're not going to find those things. Usually it's empirically driven. That's just a fancy way of saying, what do the results say? Did it get better? Did it get worse? If it got better, good. Simple as that. Now, any questions about any of that? I would highly encourage you to try that little exercise, okay? Typically we would have done it here, but I just don't think it's practical today. Here, another thing I wanted to bring up, for those of you that, like, you might be looking at, like, look at this code right here, right? 1 point crossover. You'll see that I'm picking a random number, and then I'm passing it to 1 point crossover, okay? Now, to be clear, this is not an evolutionary algorithm thing. This is a software design thing, okay? There's good code and bad code, right? If you've had me for intro programming, you certainly know this is something I emphasize. Being correct, I don't care. It has to be correct, and it has to be good code. What's good code? I don't know, but I'll know it when I see it. And I know what bad code is when I see it too. So, this is a design decision, and it is a good design decision. You might be looking at this and being like, look, if I'm getting a chromosome, like I'm giving it the mating pool, right, at an index, meaning I know what the chromosome is, I know how big the chromosome is, right? So why not just have 1 point crossover, have it the first thing it does, take the chromosome length, select the random points, and then just do it, okay? Why not do it that way? Why calculate it first and then pass it as an argument as opposed to just do it in one shot? This just seems like you're taking extra steps. Here's why. There is a couple of reasons why this is a good thing, but I'll keep it short. Again, this is a design decision. It wouldn't be wrong to do it the other way, but in my opinion, and in many people's opinion, it's definitely not as good as this way. Here's why we're doing it this way. First and foremost, we want our functions, 1 point crossover is a function, we want our functions to be as like pure and like straightforward as possible. Input, output, right? Now, when we're doing it this way, it's not that the function's not pure. I'll erase this. Kate, can you see what I draw over here? Okay, good, all right. It's not that it's not pure, but we've effectively added a dependency to our function. Now, having a dependency, okay, first let me explain what that means. A dependency is, here's what I did. I had like A, some rand thing, and then B is crossover, whatever, X, Y, and A. A simplification of what I just did, right? Right? This function, as it is not dependent on getting a random number. This function is dependent on getting a number. How we got that number, I don't care about. We're going to want a random number. That's what we're going to want. But the point is, it's not inextricably tied to this. If we go look at the crossover function, sometimes you see like X over for crossover, and we go inside and there was the rand in there, it called rand, suddenly this code, this function depends on the random number generator, okay? Now, if you have code that has a dependency, that's not necessarily a bad thing. There's a lot of ways you can get around it. One of it is do what I did, just take it out and pass it along, fine. But sometimes it just happens, and when you have a dependency that's from the standard library, which rand is, on the scale of how bad having a dependency is, something from the standard library ain't a big deal, okay? But it's still a dependency. So it's better to take it out. It's better to have like, there's nothing wrong to have a function call another function to call another function, but there's something nice about having a function, getting the result, passing it to this function, getting a result, and then passing it to that function. It's a little bit cleaner. And it's also a lot easier to test. That's a big thing. In fact, all of my code has like unit tests for it. I can test this, but I would have to do like this stuff called like monkey patching, where I basically like spoof this function to be like, okay, test this, but pretend rand is going to give you this. You have to like basically hijack what that function is going to do. It's kind of gross. Where if I just test something like that, well, that's easy. I can just put whatever number I want there to make sure it reacts properly. So there's testing reasons, there's design reasons. There's a lot of reasons why doing it that way, I'm doing it that way. If you just did it the other way, fine. But it's definitely, in my opinion, better to do it this way. The only reason I'm making a stink of this is a lot of times students who look, these are things that you wouldn't know until you've got like a lot of experience programming. So I don't really have a lot of experience programming. I'm a prof, I'm not a software engineer. I'm a prof that does more data than software engineering. But when there's something I'm aware of, I'm going to want to show you and kind of like explain why this is a good design decision. If and when you get a job, your colleagues are going to be like, yeah, do it that way. You submit your pull request, your colleagues are going to be like, maybe remove that dependency from your function, right? Again, nothing wrong with it, but I'm showing it to you now because often new programmers, this is not something you really think about as having a consequence. And most of the time, these decisions don't really have consequences until your programs really scale, which at this stage, they're not. But it's good to have these good habits earlier than later. So I'm just explaining it. It's the same thing with a lot of things in this course. Selection worked the same way. Mutation worked the same way. Remove the dependency. Yeah?
Yeah, and like, you also might be able to reuse that function for something else. Like,
Absolutely.
Say you wanted to, like, the crossword point, you wanted to use some heuristic to find it.
Mm-hmm. Think of it this way, too. As soon as random gets into there, like let's say for some reason I know, like, where is this function? Where's one-point crossover? It's not in this file. It's in another library. For all I know, this is some library I don't have direct access to. But let's say in that library it uses this. But let's say you know what? I want to be more likely to pick numbers from the first half because that's going to have a positive effect for whatever reason, right? But it's entirely reasonable to say, I want it to be random, but in a certain way. So I can do my own thing. But if this is hard-coded inside of this function that I have no access to, it works the way it does. This actually gives me far more flexibility. So there's even another reason why this is a good thing. So scalability, this really does come down to a lot about scalability. Yeah. All right. Yeah, that was that. Oh yeah, ad blocker. Great. Cool. Any other questions? That was a good question, good chat. Any other thoughts, concerns, observations, points, comments, anything? No? Everyone's happy? I love it. Cool. So yeah, for those of you that are new here, fork the repo. You're master's students, this should be trivial for you. Fork the repo, get it up and running. If you're on Windows, I recommend using PyCharm, but you can use whatever IDE you want. If you're on Linux, you can use PyCharm. You can use whatever IDE you want, just make sure it works. You might have to modify some of the paths just because of how PyCharm is set up. But if you read the README on the GitHub repo, it shows I've got like a copy and pastable bash script. Also for Windows too, if you have Python set up right. I don't. It's fine, yeah. But there's a copy and pastable bash commands that will automatically create a virtual environment for the course and download all the dependencies for the course, and you're good to go. You should be able to hit run. It should work pretty easily. Cool. All right. Now, what have we seen so far? Well, actually, hold on. Origin. I guess it's an origin where I get to have the fun. All right. Problems. Now, I made a big point. Okay, what have we seen? I showed you that high-level overview of that, just that like that figure with the loop in it, right? That really is an evolutionary algorithm. Then we talked a little bit about like what is a GA, the most basic form. It's not. I was just talking earlier today. It's not like the quintessential evolutionary algorithm, but it is. Okay, it's not the definitive evolutionary algorithm, but it is. I feel like almost all people that do evolutionary algorithms will compare every other evolutionary algorithm to a GA because it's so like basic. That doesn't mean trivial. It doesn't mean not effective. It means basic. Often simpler is better. We know that, right? And remember, the big messaging in this course is you don't want to have to use evolutionary algorithms. You hope the problems that you have don't require to use these algorithms. There's a million reasons why you don't want to use evolutionary computation. But at the end of the day, sometimes push comes to shove, you got no other good options, you try it, right? That's the types of problems we use this for. So we saw a GA, we played with it a little bit on a very silly little problem of optimizing, effectively maximizing the number of ones in a list of zeros and ones, okay? It was a simple problem. You would never use a GA for something like this, but it's just here for demonstration purposes. So now, let's start to talk about like, okay, where are we going to use these things, okay? So yeah, like I was saying, evolutionary computation is a strategy that's best kept as like a last resort. It's computationally expensive, very expensive, okay? It's often, depending on the type you use, it's quite difficult to understand your results or algorithms, especially when comparing it to other algorithms. And depending on the problem and what you're doing, it's notorious for overfitting. All of these reasons why you just don't want to use it. There's more reasons, but you just don't want to use it. Now, like I was saying, we use that toy problem, but it's important to take a moment, step back, and just give you an idea of like, okay, what problems would you actually want to apply these to? Often we're talking about like NP complete, NP hard problems. Do you know what that means? No? No? Okay, that's definitely, if you're a computer, that's definitely something you guys should definitely know. If you're the master's students, you absolutely should know that. The undergrads haven't out until your fourth year. Then, okay, you should, have you taken 455 yet?
455?
No, 355. No, 356.
I've taken 356.
You almost certainly will cover these things in 355 and 356.
I'm currently in 355, I've taken 356.
And you didn't cover this in 356?
I don't think we covered in 356.
You learned about Turing machines, right?
Yes.
Yeah, you definitely learned this.
Well, maybe. Wow.
This is like the big deal in computer science. Don't you know that like joke, does P equal NP?
That joke was mentioned.
So you definitely covered this stuff.
Well, I don't know
Okay.
if I covered it, but it was definitely that.
There's no way Dr. Smith did not talk about this. There's no way. All right, anyways, jokes aside, okay. Let's take a step back and think about problems, okay? Forget evolutionary computation for now. Let's just think about problems. In fact, we're going to think about problems in kind of like a silly way. We often don't really think about problems like this because this is so like trivial that we kind of take a couple steps past it, but let's just slow down and think about what's going on. So, systems, okay? So here's an abstract general system, okay? Often, not always, but often, systems receive some input, something happens here, and maybe some output happens, right? Okay, that's often what's going on. Cool? This isn't groundbreaking. This should be like, yeah, I kind of figured that out when I was this big, right? You just probably never really thought about it like that, but we've got some input, something's going on, some output, you know, that's kind of what's happening here. So here is a simple black box representation of a system. Black box means, I know this is literally a white box. It just means that I don't really know what's going on in here. That's fine. Maybe I can observe the input, observe the output, but there we go, right? My brain, right? You can't see my brain. You don't know what's going on in my brain, but like I can receive input, my senses, and I can produce output like I'm talking at you, I'm moving, right? What's actually going on in my body? I don't know. It's hidden by my skin, but something's going on. The system receives some number of inputs. Sometimes there's no input, sometimes there's a lot. It performs some operation on the input, some number crunching, something's going on. And then maybe there's some output that the system produces. And thinking of a system in this very abstract way helps us distinguish three important components. For concrete examples, let's consider calculating a grocery bill. The input is, well, the items, or let's say the prices of the items that I want to purchase. Okay? The model is really simple, just sum up the things. And the output is the grocery bill. Maybe there's some fancy stuff where we have to do some sales tax calculation too, but at the end of the day, very simple system. Let's say you want to design an aircraft wing. Okay? I'm some aerospace engineer. I want to design an aircraft wing. So my input, like, I'm probably doing some like modeling or something, right? So let's say I've got like, okay, I want to design an aircraft wing. So I'm going to design my wing. I'm going to simulate something on it with like these equations of complex fluid dynamics over the wings. And then at the end of the day, I'm going to get like drag estimates and lift and whatnot, okay? Okay, like that's the system I'm going for. And then like photosynthesis. Input, light, carbon dioxide, water. The model is light reacting in the plants, and the output is oxygen and sugar. The plants exhale oxygen and produce their own food. Cool. And calculating the time it takes to drive to work. Input, what route are you taking? Model, our environment. And output is, well, the time it took. Right? I'm sure you can imagine, well, I can take that route or that route. Which should I take? Well, if I go that way, it'll take longer than this way. Okay, there you go, right? These are things that we're always doing. This is trivial. Kids know this, but we don't often talk about it like this at kids. We're thinking about this very abstractly, like what's going on. So as computer scientists, we often like to think of these systems, we like to like model them as a function. In fact, you might look at this and be like, oh, I thought I was going to say function, right? Functions receive input, produce output. Great, right? Now here it says model, but like we're modeling these things. So we are often taking these real world things, and if we want to use the fancy Latin words to sound smart, we could say in vivo. That means like in like real life. And we try to model these things in a computer. And this is a 20th century Latin word that the Latin people never use, but we like to sound smart and we say in silico, okay? I'm never going to use those again in this course. I hate it, but you see it all the time in the literature from scientists trying to sound smart. But in silico, ooh, in the computer. Okay, yeah, great. All right? So we are modeling real world things as these functions. A model is just like the function. Now, sometimes, okay, that's what we have. Now you might look at this and be like, well, actually there's kind of like three distinct parts of this system, right? The input, the thing, here I'm calling it the model. The model is a very abused word in computer science. The way I'm using it here is like a model would be like the complex fluid dynamic equations that exist in our universe, but I've calculated it and I can run it on a computer. The model is the fact that like I'm not literally running it through our universe, but I'm like simulating it. That's the model, okay? We love modeling things because things are expensive in real life. Okay, so there's three distinct parts, the input, the model, and the output. And sometimes what we care about is one of those three parts. Actually, often the thing we care about is one of those three parts. So, let's say we have an optimization problem, okay? Optimization takes place when I know the model, it's easy, and the output is like specified. Sometimes the output might be something as clear as I need the numbers to add up to 77, and sometimes the model or the output is, or the desired output is I want the shortest time to work, okay? The question then is, what input gives me what I want? So the goal is, what's the input that I want? I want to optimize something. If you read assignment 1, TSP, what is the pathway I take to minimize the total distance? The model is the total distance of the Hamiltonian cycle. What I'm looking for is, find me the smallest one. The input is, well, what path do I take? I want to find the path. So the search space in this particular case is the set of all possible inputs. Now, often we try to actually, we'll talk about this shortly, we often try to prune this as much as possible because sometimes the set of all possible inputs, just because it's a valid input doesn't mean it would be an admissible solution. Like think TSP. You want to visit one city, each city once and only once unless it's the starting city, right? Right, it has to be a permutation. But technically, like we could say go to city 0, then city 0, and then city 0, and then city 0, right? Like you could say that, but you don't want to say that because you're actually kind of like, that's wasteful, right? Anyways. So for example, finding a path to work results the smallest distance. The search space would be all possible paths to work. Often we can trim that pretty easily. I'm not going to get from my house to work by going through Toronto, right? Not going to happen. We can trim this down quite a bit. It is one of the possible paths to work, but we don't even need to consider that one. Obviously, it's not going to be good. Anyways, assuming living and working through town, yeah, don't go out of town. Don't go to New Glasgow to get to, unless you live in Truro or something, right? So TSP, traveling salesman problem. All right, so the traveling salesman problem, classic optimization problem. It's like a toy problem. When I say toy problem, one time someone left a comment on one of my YouTube videos once and they got really mad about the fact that I called it a toy problem. And they completely misunderstood what I was saying. When I say toy problem, it doesn't mean it's not helpful, it's not worthwhile looking at or anything. No, I mean it's such an easy to understand problem. To be clear, this is a hard freaking problem. It's actually NP hard, which you obviously know. But yeah, TSP, it's really hard, but that doesn't mean it's not worth studying. We like to use it because it's easy to understand, but it's really hard. And it's a great benchmark. But we'll pick up here next time. See y'all later.